Hey guys, hello everyone. Welcome to Unacademy, all of you, and we are here with another very important session, guys. So, in this session, we are going to discuss the important name reaction. This is a revision series, so we are going to be discussing four important name reaction along with their examples. Okay. So, yes, guys, we have already had started a strategy series before the revision series, right? We have also had some important name reactions in the organic name reaction series, and we are going to continue doing so in this session, right? So yes, what can you expect on Unacademy right now? What is going on? So if you visit my profile, you will be seeing two important batches, right? That is chemical sciences CSIR-NET. You are going to visit my profile, you will see impulse detail batch, and this batch has started from June 22. And in this batch, I am taking all the important topics of organic chemistry and inorganic chemistry. Nurul sir is taking important topics of physical chemistry. Okay. Now this is a detailed batch as you can see, and along with this, just after 1 month from July 21, I have started another new important course, Chemathon practice batch. Now this is a practice batch. Okay. Starts from tomorrow. All right. From 21st. So detailed batch and practice batch both are going on right now. If you want, you can enroll. If you want, you can join. These are plus courses. Okay, so plus courses means you have to join an Academy Plus subscription, right? These are all subscription courses. So how are you going to join right now, guys? A very nice offer is going on an Academy Plus. That is, if you are using my code, that is Jagriti S Live, that is going to give you a 20% discount right now between 18 to 22nd of July. Otherwise, usually guys, usually you get only 10%, right? By using this code, you only get 10% discount, but right now you are going to get 20% discount on the same code in between July 18th to 22, right? And my course is starting from 21st. So it is very important that you join right now, okay, by using the same code. So we are going to move onwards everyone, and we are going to start our discussion on important name reactions. And let me also inform you what about the free classes. So free YouTube session, you are going to see me on YouTube. Usually our timing is Friday and Saturday. This is our usual timing, Friday and Saturday, 9:15 a.m. let's say. Okay, and we have already had a strategy series. Now we are doing a revision series. Okay, so we are revising important name reactions and reagents. And what about these classes? These are also free sessions, but they are on Unacademy. They are special classes, free classes. We are doing battle of poles, as you can see, which means all practice. Okay, so we have done pericyclic, photochemistry, organometallics in this month already. We have done these three topics. From tomorrow we are starting bioinorganic. Okay, so bioinorganic, carbohydrates and amino acids, all important topics. If you haven't yet done these topics, please do them quickly, and just by solving previous year questions you will be able to get a lot of things. Okay, you'll be able to understand a lot of things, right, about this. So don't forget to join me on Unacademy 6 p.m. every day. Okay, chalo. So yes guys, let's start our discussion. Also don't forget to join me on Telegram. This is my channel name, CSIR Net 2022. Okay, this is my Telegram channel. You can join up directly. So what are we going to discuss, guys? Which reactions are we going to discuss in today's session? We are going to discuss Mitsunobu reaction, Peterson elimination, Baer-Villiger oxidation, and Dakin reaction. All of these important name reactions we are going to discuss in this particular session. Okay, let's start with Mitsunobu reaction first of all. Okay, guys. So Mitsunobu reaction, as it is a very simple reaction. Okay, it's a very simple and direct reaction. What are we doing over here? It is often sometimes known as modern SN2 reaction because it is only an SN2 reaction. If you see, let's say you are having a molecule in this way. This is your R and R dash. Both of these are different groups. One of them is hydrogen below, and above you are having this alcohol group. Okay, so usually the replacement of this alcohol Alright, I am writing another molecule. The hydrogen is above this time and the OH has gone below. So what has just happened looks like that one OH minus over here, one OH minus has just substituted this OH minus, isn't it? Right? And that has done a SN2 attack. One OH minus has done a backside attack on another OH minus. Looks like that, okay? So there is a lot going on, and it's not just directly OH minus. So what are you going to take first of all? You are going to take a protonated nucleophile in the presence of phosphine. And originally triphenyl phosphine was taken, so we are going to take triphenyl phosphine and diethyl azo-dicarboxylate molecule, dead molecule. Okay. So all of these three things, whenever you see an alcohol, an inversion, and these three combination, you are going to know it is a Mitsunobu reaction. Alright, so what is a dead molecule? Let's see that first. Diethyl azo-dicarboxylate. Okay, so it is diethyl azo-dicarboxylate. This is your diethyl azo-dicarboxylate. Okay, not too here. Okay, this is correct. Right? So this in the presence of phosphine and nucleophile. So guys, let's see what is about to happen. What is the mechanism? Let's see quickly once again, since we are revising. Many of you might study this reaction for the first time, so pay attention. So on this dead molecule, guys, let's say I'm writing COOET, N double bond N, once again COOET. Okay, so on this dead molecule, phosphine is going to attack first of all. In this way, attacks the nitrogen. Absolutely, this bond opens up. This bond is going to open up, and it is going to get a proton. Where does it get a proton from? From the protonated nucleophile. All right, and now the nucleophile is free over here. Okay, so it has become COOET. One nitrogen has got the phosphine PPH3 positive. Another nitrogen has got a proton CO2ET in this way. Alright, so what happens, guys? The nucleophile is free, the alcohol is there. So phosphorus has a great affinity for alcohol. So this OH group, this is absolutely going to attack on the phosphorus. As you can see, you are having an alcohol. Let's say I'm directly writing above. So this OH is going to attack over the phosphorus. The bond is going to open up. It is going to take one more hydrogen from this alcohol, and it is going to become this molecule. What are you eliminating? You are eliminating protonated dead molecule actually. This is eliminated. You don't need it anymore. And what do you need? You need that your alcohol has just formed the phosphonium ion. See, like this. So alcohol got connected with phosphorus, and this is what you have. Alright, now where's the nucleophile? This is your nucleophile, guys. Nucleophile was free. Nucleophile was free right over here. Right? So in this step, the nucleophile has become free, but it cannot directly attack on the alcohol. Why? Because OH was not a good leaving group. Now in this step, you have made OH a good leaving group. So in the next step, now it can attack. Now it can give you a attack like this. So let's write it in the next page. If a nucleophile attacks, this is R dash, you are now going to have dashed nucleophile. That is, the nucleophile has attacked from below the plane. Okay. So alright guys, this is your nucleophile. Now who is the nucleophile? That is some oxygen source only. Alright, we will discuss over here what can be your nucleophile. Many a times your nucleophile is given to be benzoic acid or paranitrobenzoic acid, something like this. Okay, so this is your nucleophile. For example, paranitrobenzoic acid. Alright, so the proton is removed from the nucleophile, then you can say that this molecule is going to look like this. All right. So this is an ester molecule. What happens in the final step? In the final step, we want to hydrolyze what we have got over here. So we have already got the SN2 product. The nucleophile has attacked, and the oxygen, the alcohol group OH has left out. Okay, SN2 has already taken place, but here we want to hydrolyze this. Let's say in the presence of a base, it's going to be faster. In the presence of a base, you're going to get a faster reaction. It will be OH over here. OH minus attacks on this carbonyl, right? So bond opens up. So you'll have O minus and hydrogen is above. This is your product. Okay. So Mitsunobu reaction gives you the inversion product basically. Alright, very, very important for all of you to know. This has been asked plenty of times in your examination. And one very, very, very frequently asked example that you will see in your paper is, see, look at this question. Alright, you are having a methyl and you have a double bond over here. Sometimes this is asked, sometimes alpha pinene is also asked. Alright, it makes the question even more difficult. Alpha pinene is asked over here. Alright, so what are we doing? First step is hydroboration, let's say. So hydroboration BH3, if you are adding borane to it, BH3 and H2O2 in the next step, right? So hydroboration and oxidation will absolutely give you the syn product. That is, it is going to add. Now see guys, this these two carbons, these two methyls are above the plane. They are causing steric hindrance. So definitely the hydrogen is and the oxygen is going to be added below. So we can directly write this methyl is above, hydrogen is below, and the BH2 is also below. In the next step, that is of height of the oxidation H2O2. If you remember the mechanism of hydroboration oxidation, you are going to say that the boron, wherever it is, there only OH will be present. Alright, in the oxidation step, there is retention in stereochemistry as it is the OH will be applied over here. Now, if you are providing to this molecule, if you are providing paranitrobenzoic acid, alright, phosphine and dead molecule in the first step, and in the second step lithium aluminium hydride, let's say, what are you going to get? You will get this molecule. Methyl is above, the OH will also go above. What has just happened? Reversal, that is the SN2 attack of the OH on another OH, like that. Okay, so Mitsunobu reaction, inversion on the alcoholic group. So this is a very important example. Just like this, many other examples are also available. Just visit the previous year questions. You are going to see plenty of examples under this reaction. Okay. So now we are going to talk about another important reaction, guys, that is Peterson olefination. Okay. Another very, very important reaction is Peterson olefination. Now guys, what is olefination? See, when we are actually breaking a bond, when we are breaking or let's say when we are making a double bond from a single bond, either we are going to do E1 type elimination or E1CB type elimination. What is Peterson elimination? You are getting an alkene, from alpha stylyl carbanion basically. Okay, alpha stylyl, or you can write alpha stylyl carbonyl compounds. Alpha stylyl carbonyl compounds. Okay, yes, very, very important. Let's see an example. So Peterson elimination or olefination, we are just directly going to see with examples only. right? So let's say you are having CH3, C double bond O, and CH3 once again, let's say. Alright, let's keep it simple. One carbonyl. Another thing that we are going to do is, let's say you are having, let's not write it like this. It would be easier to already have this molecule. OH, SIME. Okay. So what's the whole point? The point is that you are taking alpha silyl carbonyl compounds, right? Alpha silyl. Okay. So you would actually better call this molecule as alpha silyl hydroxy compound. Okay, not carbonyl, hydroxy. Okay. Now, how are you synthesizing this molecule? That you can say that you are starting from carbonyls. Let's say you started from this carbonyl, and let's say you are having a carbanion which has SIME3 group. Let's say which carbanion is required over here, this one. Alright, so let's say you're having this carbanion, it has attacked over here, you got this alcohol. What is this molecule? This is your alpha phenyl alcohol. Okay, this is what you end up with. Alright guys. So once you have got this molecule alpha phenyl alcohol, now the selectivity begins. Right, so what is the selectivity guys? Selectivity is of the medium, acidic medium or basic medium. Right, that is when we need to understand, that is what we need to understand how it is going to react. So for understanding the selectivity and the type of product, I will consider two different substituents. Why? Then only you will be able to understand the product formation. Let's say I'm considering CH3, C2H5, and SIME3 over here, and once more CH3 and C2H5. Let's see, this is what we are going to consider. Okay, what happens in the presence of acid and base in heat? Alright, so first thing guys, if you are having let's say C2H5 below the plane, CH3 above the plane, and OH like this, SIME3, CH3 above the plane, C2H5 below the plane. Let's say this is one isomer of the molecule. What I have done is I have deliberately kept OH and SIME3 anti. So what will happen guys, if I do the reaction, the olefination in the presence of a base, OH minus, what is it going to lead to? OH minus in the presence of a base guys, it is going to take away a proton from the alcohol. Alright, so C2H5, right, I have to see what happens next. So after removing a proton guys, what will happen? This molecule is going to be, right, very interesting this one. This molecule becomes O minus, oxide. Now this oxide will not form an epoxide over here. Don't try to just attack this carbon and remove the SIME3. That's not going to happen. Okay, it's not a good leaving group. So what will happen is this oxygen will try to, oxygen has a great affinity for silicon. So it will try to pull the silicon towards itself. Okay, so I have to rotate the other molecule, other carbon, I have to rotate. So this methyl goes below and C2H5 comes above. Alright, now the oxygen is going to attack over here. It's going to form a four-membered ring which is going to break down to give you this kind of an alkene. Just pay attention guys, who is present together, C2H5 and CH3. These two groups are present together. Okay, so what is an alkene that I get? I get a trans alkene or a E alkene, right? So what is important is which condition, how is the elimination taking place? This is a syn elimination reaction, guys. Why? Because we see that both the groups are eliminating from the same side. It is a syn elimination reaction in the presence of a base. So basic condition will always give you syn elimination. Whether you get trans alkene or E alkene, that depends on the molecule, which kind of molecule you have taken, right? So for this system you get trans, maybe for it's another isomer you might get cis also, but remember in the basic condition you get syn elimination. This is what you have to remember. Okay? Now, the same molecule I'm going to take in the presence of acid. What will happen, guys? Same molecule I'm taking in the presence of acid. It will become OH2 positive, isn't it? In the presence of excess of acid, it becomes OH2 positive. Yes. Now, somebody has to attack over silicon. If the oxygen has become positive, it cannot attack over silicon, right? So somebody has to attack over silicon. Who is going to do so? Who is going to attack over silicon? Water. Okay, so this is not the intramolecular reaction. If water attacks on silicon, the bond is going to open up like this, and it's a very good leaving group. The OH2 is a very good leaving group. So in this case, you are going to end up the same molecule I had taken over here. In this case, you are going to end up with a cis alkene, alright, or Z alkene. What is the kind of elimination? The elimination is anti-elimination. Okay. So just by taking the same molecule, I've taken the same molecule over here in the presence of base, you are doing syn elimination. In the presence of acid, you are doing anti-elimination, and that is why different products. So this is the selectivity of Peterson elimination. It depends on the condition, right? It depends on the condition which you are taking, and based on that you're going to get the products. So let's look at one molecule as an example, guys. It's a very popular example over here. In one cyclic molecule you have everything basically. See, you are having SiMe2pH, for example. Okay, this is an OH which is below, and there is an OH which is above. Alright, so this is your molecule. There's one more OH over here. Now what is going to happen? What is going to be the product in the presence of a base? Base could be anything. You could have a KHMDS base, you can have a butyl lithium, alright, or NaH. NaH is also good enough to remove this OH proton. So any of the bases you can take over here. In the basic condition, what will happen? You must remember basic condition gives you syn elimination, which means you are going to find an oxygen which is on the same side, and you are going to eliminate both of these groups. So which oxygen, which alcoholic group is on the same side? These are all protected alcohols. Yes, so on the same side, it is this OH group, which means the first product that you get is right over here. It is the product of syn elimination. Now, doing the elimination in the presence of acid, how is it going to work? Acid elimination is anti-elimination. Just remember, guys, in the presence of acid, you have anti-elimination. A for acid, A for anti, right? You can remember like that. So which is the anti-alcohol? This one on the opposite side. So what is going to be the product? This OH2 is going to leave, and you are going to get a double bond over here. Very, very, very important application of this reaction, Peterson olefination reaction, on this particular example. Right? Yes, very well. So I hope that we have understood this reaction nicely, guys. Now we are going to discuss a very important and very simple reaction, that is your Baeyer-Villiger oxidation. So Baeyer-Villiger oxidation is one of the most frequently asked uh, reaction, but yet sometimes we tend to be doing wrong answers in the Beverly. We tend to give wrong answers in this simple name reaction also, right? So Bear villager oxidation. Let's quickly talk about this. So what are we doing, guys? In the Bear villager oxidation, you are oxidizing a ketone R C double bond O R dash, a ketone with any per acid, right? It could be any per acid. Per acid includes CH3C triple OH, that is your peracetic acid, or metachloro per benzoic acid. Alright, any per acid you can take, or you can also take H2O2 in the presence of acid. It will, all of them are going to provide you electrophilic source of oxygen. Okay, so what is the mechanism, guys? What is happening? Let's say you are going to get the ester. So you start from the ketone and you get the ester over here. Okay, so what is the mechanism which is happening? Let's take an example, guys, because when we see an example, we are able to see the selectivity better. Okay, so I'm just taking the example of CH3, C double bond O, C2H5. Okay, so yes, what happens is I am providing metachloro, or let's say CF3COOH, या फिर CH3C triple bond OH like this. Peracetic acid I'm providing. So what's going to happen in the presence of peracetic acid? First of all, this oxygen is going to get protonated and it is going to get a positive charge. CH3, C double bond OH, positive charge, C2H5. Yes, what happens is now you have CH3, C double bond O, OO minus in this case. So this O minus is going to fall over here, the bond opens up, alright, and you are going to get a tetrahedral intermediate OH and C2H5, and you have oxygen, oxygen, one carbonyl, and the CH3 group. So this is your tetrahedral intermediate that you have. Now when the intermediate falls back, one of the group is going to migrate. Who is going to migrate? That based on the migratory aptitude, C2H5 group is going to migrate on this oxygen. Now this oxygen is known as electrophilic oxygen. Alright, so this bond is going to open up from here and you are finally going to have this oxygen inserted in between the carbon bond, which is more substituted. So this is a more substituted bond. This is a more substituted bond over here. So exactly over this position, the oxygen is going to insert. All right. So this is very, very important about Beer-Villager oxidation. Most of the times you're going to see that the more substituted carbon migrates. So if we are directly able to write the products of some of the reactions, let's see. Example number 1. In this case, example number 1 is like this: metachloroperbenzoic acid. Okay, in the presence of CH2Cl2, which is just a solvent. So you can tell me which side the oxygen is going to insert. It is very obvious that on the more substituted side, that is on this side, your electrophilic oxygen is going to insert and you are getting a 7-membered ring. In this case, both the methyls are as it is. Okay, so this is your major product. Major product, always the ester will form on the more substituted side. So let's say now we have a ketone molecule, pentanone molecule. Alright, so once again doing the same reaction on pentanone is going to give you a 6-membered ring, and this is going to be your product once again. Major product where the more substituted carbon has migrated. Now let's look at the a cyclic molecule. Let's look at this molecule over here. So this molecule in the presence of same metachloroperbenzoic acid or peracetic acid or CF3COOH. This is also per trifluoroacetic acid. Where is your oxygen going to be inserted? This is the primary carbon, this is the tertiary carbon. So absolutely you are going to draw the molecule in such a way that tertiary carbon is going to insert the oxygen. This is your major product. Okay. So I hope that it makes sense that how the reaction is taking place. Bare villager oxidation is again a very simple reaction. All right. Now guys, just like this, just like a bare villager oxidation, you have one more reaction which has been asked plenty of times in your exam. Okay, slides are over, so we have to go back and clean up, right? So, fourth reaction, very important, is Dakin oxidation. Fourth reaction, very important, is Dakin oxidation, right? So, what is Dakin oxidation, guys? It is a special case of bare villager oxidation, just that. So, whenever you study bare villager oxidation, also study Dakin oxidation. It is just a special case. Okay, so what is happening, guys? The aromatic compounds, let's say you are having a aromatic aldehyde. So aromatic compounds, if you are doing the same thing, H2O2 in the presence of OH minus, the only difference is that you are using a base over here. Beveridger oxidation, you had used a per acid, but here you are using a base. Alright, what will happen, guys? It is going to give you a phenol. Alright, so it is going to give you a phenol. Along with that, the formate carboxy radical. Okay, what is the mechanism? Let's very quickly see what is happening, guys. If you are using OH minus, this OH minus is going to create a peroxy anion. This will attack over this carbonyl and the bond is going to open up. What does it give you? It gives us the tetrahedral intermediate once again, O minus, and a hydrogen and this anion. So what is going to happen next? The negative charge falls back. The aryl group is going to be transferred onto this oxygen. You are having minus OH minus from here and and oxygen C double bond O and H. So what have you got? You have got formate. Okay, you have got a formate ester, but phenyl formate ester like this. Now, once again, the base is present. It is going to attack over this carbonyl. The bond is going to open up on this side. You have got a phenol. You have got a phenol O minus, and along with that, you have HCOOH. So obviously there will be a proton exchange. The acidic proton is going to be taken away by the phenolate ion, and you get this product. Now, where is this question asked? Where is Dakin oxidation asked? It is asked various times, right, in combination with the Riemer-Tiemann reaction, right? Let's say you have got this alcohol phenol molecule. So in the presence of CHCl3 and NaOH, that is your combination for Riemer-Tiemann reaction, you get formylation. You get formylation, you get orthoformylation. And now if you are adding H2O2 and OH minus, you are going to get not oxidation, you are not going to get COOH over here, you will get catechol. Alright, so it's a very important reaction that you remember this Dakin oxidation, special case of Beveridger oxidation only, very similar to that, but here you are using a base and here you are using aromatic aldehyde, not a ketone. Okay, and that's why you end up with the phenol molecule. Alright guys, so these were four important reactions which have been directly asked in your exam that we have discussed over here, and many more reactions are going to follow. Do watch all these sessions. Thank you so much. And if you are liking all the content, please follow our channel because we are working all for you only. So bye everyone. We'll see you very, very soon.